Hey, I want to talk a little bit about errors. And when we say errors, we often think of slovenliness or oversight. That's not the case here. Errors cannot be avoided in long-term hypothesis testing. And let me tell you about the type of errors I'm talking about. Hypothesis testing is an inferential process, which means that it uses limited information as the basis for reaching a general conclusion. Specifically, a sample provides only limited or incomplete information about the whole population, and yet a hypothesis test uses a sample to draw a conclusion about the population. In this situation, there is always the possibility that an incorrect conclusion will be made. Although sample data are usually representative of the population, there's always a chance that the sample is misleading and will cause a researcher to make the wrong decision about research results. In a hypothesis test, there are two different sorts of errors that can be made. Here's type 1. A type 1 error occurs when a researcher rejects a null hypothesis that's actually true. In a typical situation, a type 1 error means the researcher concludes that a treatment does have an effect when in fact it has no effect. Now, why the heck might they think that? Well, a type 1 error occurs when a researcher unknowingly obtains an extreme, non-representative sample. Fortunately, the hypothesis test is structured to minimize that risk. And figure 8.5 shows the distribution of sample means and the critical region for the waitress tipping study we've been talking about. This distribution contains all the sample means for n of 36 if the null is true, and this is earlier in the chapter. Notice that most of the sample means are near the hypothesized population mean of 15.8. With an alpha level of 0.05, only 5% of the samples have means in the critical region. Therefore, there's only a 5% chance that one of those samples will be obtained essentially by accident. This is an important sentence. The alpha level determines the probability of obtaining a sample mean in the critical region when the null hypothesis is true. And this is the most important sentence. In other words, the alpha level determines the probability of a type 1 error. If the null hypothesis is true, what's the probability of getting one of those means out there in the tails or in one tail accidentally? Just 5%. If the null hypothesis is true, the probability of rejecting it when the null is actually true is only 5%. Of course, if we chose alpha of 0.1, it's only 1%. So that's comforting. The alpha level for a hypothesis test is the probability that the test will lead to a type 1 error. Absolutely. That is, the alpha level determines the probability of obtaining sample data in the critical region, even though the null hypothesis is true. And I'll get back to type 2. Let me just say this real quickly. Let's say I was testing a drug that had a really awful side effect, and who knows what that is. In the early days of antidepressants, they had horrible side effects. And this wasn't that long ago, 30 years ago, late 80s. In that case, I would be cautious. I wouldn't want to get an experimentally significant result by chance, and that might motivate me to use alpha of 0.1, the probability of a chance result yielding to rejecting the null hypothesis being only 1%. And I might want to insist on doing that, particularly if the drug has awful side effects. And we've had some drugs in their infancy that had awful side effects. I think it was Prozac that had some, and this is years ago, some violent side effects. So in that case, that might be one particular reason why you would choose a lower probability of a type 1 error.